First of all, is the sky blue?
Yes.
Okay. Well, at least we got that out.
Does it look blue to you?
It does.
Fine. That's what we're about to talk about.
All right.
Okay. So, here's the deal. The explanation is actually simple. It just takes a little while to explain.
Okay.
That's all.
All right.
All right.
I have time.
You have time.
I have some time.
Thank you. Thank you.
Yes, and boom.
All right. So, we have an atmosphere.
Okay.
We all know this.
Yes, we do.
Okay. It's composed primarily of nitrogen.
Okay.
It's 78% nitrogen, it's 21% oxygen, and a few percent other, carbon dioxide, this sort of thing. Mixed in there are particles of like pollen and dust and sand from sandstorms and pollution and smog. And so
Particulates.
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 Okay. Now, light comes from the sun. White light. People say the sun is yellow, it's white.
Right.
Okay.
Exactly.
You've seen the sun in the middle of the day, it's white.
It is white.
Okay? That's the proper color of the sun in the middle of the day.
Let's not get racist.
Let's
It don't have to be the proper color.
Look, it's just a color.
It's just the color.
Damn, Chuck, why is everything a race thing to you?
Because I live in America.
All right. So, you may remember that white light is composed of colors.
Right.
Okay?
Put it through a prism.
That's how you get a rainbow.
All right.
Or you're educated, you said prism, but through a raindrop, it spreads them out into colors.
Right.
And you get the colors of the rainbow. Roy G. Biv.
Okay.
Give them to me.
Right. Red, green, blue, yellow.
Roy G. Biv, go.
Roy. Red, orange, green.
Roy, yeah.
Oh, red, orange, yellow, green, blue. And then ultraviolet, but violet.
Biv.
Okay, indigo, violet.
Thank you. Red, orange, yellow, green, blue,
indigo, violet.
Okay, the 7 colors of the spectrum. Okay, if you, the way our brain works and the sensors in your retina, okay, the rods, the cones. Yeah, the rods give you shades of light and intensity. The cones disentangle color.
Okay.
Okay, and you have an RGB cones.
Nice.
Okay, so we get RGB from.
Right.
You've heard that in computers and
right.
the computer screens and everything. Okay, so you are chemically, with the chemicals in your retina, splitting that red light into combinations of red, green, and blue.
Okay.
Okay, broad combinations of these 3. If you have more red than the others, what you look at is going to look more red to you.
Right.
If you have more blue than the others, it's going to look blue. Now here's what happens: white light comes down from the sun.
Is that what it does?
The particles in the atmosphere, some of them are about the same size as the wavelength of blue light.
Sweet.
All right. Now, if you have a particle and light, and there's a particle is the same size as that light, it'll reflect.
That's right.
Or scatter. That's the proper word. Okay. Bounce, scatter, and so that light doesn't make it straight through. It sends in every other direction.
Oh.
So the light from the sun is selectively has the blue removed on its way down to Earth's surface. And the blue scatters into the air, and you have a blue sky.
That's very romantic.
It is beautiful. Now it's called Rayleigh scattering. A guy named Rayleigh.
Rayleigh scattering.
Rayleigh. Okay? Lord Rayleigh.
Of
okay?
course, Lord Rayleigh. Indeed.
You figured this stuff out. You a lord.
Right.
All right. So here's the thing. As the sun gets lower in the atmosphere,
Right.
the path length of the light is much longer through the air. Okay? So in other words, so here's your atmosphere. If you're directly above, you're going through like this thickness. As you come down, the thickness gets more.
Right.
Okay?
Right.
Well, more atmosphere, more scattering.
Right.
The sky gets more blue. Okay? So in the daytime, it's, quote, sky blue. That's actually a pale blue.
Right, it's a very pale blue.
As you go to twilight, that sucker gets deep.
Yeah.
It gets deep blue. And so much more blue gets taken out of the sun.
I just love how violent deep blue is.
It's deep. And if you take out that much blue, the sun ain't got no blue light left at all. So what color is it going to turn?
Kind of red.
Kind of red.
Kind of red.
Kind of red, amber.
Yeah.
Okay? That's why sunsets are red.
Oh, that's
Because so much blue was taken out.
right.
That's all it has left to give you is the side of the spectrum where you have red, orange, yellow. Now, sometimes you have a very bright sunset that's not quite deep red. There aren't many particles there for that sunset. There aren't many particles.
Sweet. So that's a kind of a lighter cut, like you know.
Yeah. So the sky wouldn't get as intensely blue when that happens.
Right.
It'll be similar to the sky blue you had earlier in the day. So that's why we have a blue sky.
Nice.
Now, it's also why you can't see stars in the daytime other than the sun.
Well, wouldn't that...
It's not, oh, you can't see stars in the daytime because the sun is out.
All right.
That's not why.
Because the sun is brighter than the starlight that you would otherwise see.
No, that's not why.
Well, see, that's intuitive.
No.
That's how you would think.
It's intuitive, but it's wrong, okay? The reason why you can't see stars in the daytime is because the scattered blue light has rendered our atmosphere aglow.
Nice.
The atmosphere is glowing blue light. And that prevents you from seeing the stars behind it. If you took away the atmosphere,
you'd be able to look up and see the sun.
the sun will be there, but then you like dark adjust over here, and there's full sky, full stars right over here.
Wow.
Over there, all around.
Oh, man. You know what?
What?
If we didn't need atmosphere, I'd want to get rid of it. That kind of sucks.
Okay, so now, this is what led to the operational definition of the edge of the atmosphere.
Okay.
Okay? It's kind of operational. It is, how high up in the air do you have to go before there aren't so many air molecules above you for the blue light to scatter and prevent you from seeing the night sky?
So it's really about the number of particles.
Yes.
It's not
The density of
about
particles.
the actual...
No, it's just the density of particles, wherever that happens. So we agree, just by convention, that if you go up 100 kilometers,
Okay.
converted, it gets 62 miles, 100 kilometers, that's about where the atmosphere is thinned out, so that it's no longer scattering blue light, it is no longer a glow, and in broad daylight you can see stars in the nighttime sky. So that's the operational definition of space.
The operational definition of space is 62 miles above our ground.
Earth's surface, correct.
Earth's surface, where you can just see space, basically.
Because the atmosphere, there's still atmosphere there, but it's not dense enough to scatter blue light and render it aglow to prevent you from seeing the night sky. Now, I'm not comfortable with that. I understand it.
Okay.
I'm not comfortable.
Now, what's your problem with that?
Because if the atmosphere were half as thick as it is,
Well, then it would only be 30.
it would be
31 miles.
31 miles. That would be space. Well, suppose we're a tenth of it. Then it would be 3 miles. Suppose we didn't have an atmosphere. You'd be in space just standing here, sitting here like this. Should that be called space? That's what I'm saying. Our definition of space is linked to to the circumstances of our atmosphere.
That kind of makes sense. Well, no, I see what you're saying now, because I was about to say it kind of makes sense because you can't breathe in space, but you also cannot breathe at 35,000 feet.